In the last video, we talked about magnets as agents. This time, we're going to talk about them as objects. Remember, when we represent objects mathematically, we use lowercase letters. For gravity, we use a lowercase m when talking about massive objects. For electricity, we use a lowercase q when talking about objects with a net charge. A moving particle with a net charge could be an object, and we can write that out as little q times little v. A current in a wire could be an object, and we could write that as little I times little l. In the reading, we described the object hand rule. To use this rule, you hold your hand with your fingers and palm flat, but with your thumb sticking out to the side. Your thumb represents the motion of the object. Your fingers represent the magnetic field due to the agent, and your palm represents the force on the object due to the agent. This is easy to remember. Your thumb is the velocity of the object, like a hitchhiker. Your many fingers represent the many field lines of the agent, and you push with your palm. That's the force. In the last video, we discussed how to draw 3D vectors. I'll mention it again really quickly. This vector is going to the left, this one is going up, this dot represents a vector coming straight at you out of the screen, and this X represents a vector going into the screen. The object hand rule is three-dimensional. If I hold my hand like this, I have three axes, X, Y, and Z. X is my velocity, Y is my agent field, and Z is my force on the object. If the object I'm studying is negative, I use my left hand. If the object I'm studying is positive, I use my right hand. Let's do some important samples of object interactions in agent fields. We'll start with some simple diagrams. Here are a bunch of situations where I know the direction of the moving charge and the orientation of the external field, and I want to know the direction of the force on the object. In this picture, we see an electron traveling to the right in this external magnetic field going into the board. And if we use our left hand for the negative charge, we see that our thumb is going to the right, our fingers are going into the board, and that means our palm is going down the paper, and so that is the direction of the force on that electron. In this second picture, we have a positive charge moving toward the top of the paper in an external field. I'm going to use my right hand this time. My thumb is pointing to the top of the paper, my fingers are going to the right, and now my palm is pushing into the board. So the force on this guy is into the board. In this picture, we have a positive charge moving up toward the top of the board, and the field's also going that way. Now, notice the velocity vector and the field vectors are parallel. This means my thumb and my fingers would have to be going in the same direction, which doesn't work for the cross product. So there is zero force in this picture. In this picture, we have an electron current in a wire traveling to the right in an external field. I'll use my left hand because electrons are negative. My thumb is going to the right, my fingers are coming out toward me, and that means my palm is facing upward, so the force is toward the top of the paper. In this picture, we see an electron beam coming out toward us, so our thumb is toward us. Our agent field is to the left, so my fingers go that way, and when I do that, my palm is facing upwards, so the force is toward the top of the paper. Here are a bunch of situations where I can see the direction of the moving charge, and I can see the force on the object, and I need to infer what the magnetic field must look like. On this one, we see the velocity of this positive charge is to the right, and the force on him is toward the top of the paper. So I'll use my right hand and put my thumb to the right, my palm is facing the top of the paper, and when I hold my hand like that, my fingers are going in to the board, so I'm going to draw the agent field as X's. In this picture, we have a negative charge going toward the bottom of the paper. So I'll put my left thumb going down, and the force is into the paper, so I'm going to put my palm facing that way. When I do that, my fingers are going to the right, so the agent field looks like this. In this picture, I've got electrons going into the board, so I use my left thumb into the board. My palm is going to the right, because that's the force, and when I do that, my fingers are pointing down toward the bottom of the paper. So it would be like this. Lastly, here are some situations where I know everything except the flavor of the object charge. We see that something is moving to the right in this external x field and the force is up. So let's see, if I do that with my left hand, if I try to do that with my left hand, if I put my left thumb going right and my palm going up, my fingers look like dots, so that's not right. If I try it with my right hand, my thumb is to the right, my palm is up, and my fingers are going in, that is right. So this is a positive charge. In this picture, we have something going toward us, and the force on it is down when it's in this external field to the right. If I try this with my left hand, my thumb is toward me, my palm is down, and my fingers are that way. That works correctly. This is negative. I also want to look at two important agent-object combo situations. Here is a set of two parallel wires. Each one has an electron current going to the right. Both wires are magnets. Do these wires attract or repel each other? In order to answer this question, we have to use both the agent and object rules. The top wire is an object in the bottom wire's agent field. The bottom wire is an object in the top wire's agent field. So the way we can do that is this. Let's first consider the red guy as the agent. So he's going to make a field around him, and I can use the agent hand rule to see that he is making X's above himself and then dots below himself. Okay. Now, our blue guy is an object in that red dot field. So my thumb for the blue guy is to the right, and my fingers are going to represent those red dots, so they're coming toward me. And when I do that, my palm is going upward, so the force is upward. So we can think about this a couple ways. If we think about this from a third law perspective, if red pulls blue up, then blue should pull red down, and these guys are going to attract each other. But we don't have to do that. We can actually just check by finishing the magnetic problem. We can consider the blue guy as the agent and say, all right, as an agent, my thumb is going to the right, and my hand is showing fingers going in up here, so this is X's up here and dots down here. And now my red wire as an object is in the blue X field. And so if I do my object equation for the red guy, my thumb is going to the right, my blue fingers are going into the board, and that means my palm is going to the bottom. So in fact, I get a force that's going down, and these two wires are attracting each other. Here are two adjacent solenoids. The solenoid on the left has a cell connected to it, so it's a magnet. The solenoid on the right does not, so it's not a magnet yet. If I want the two solenoids to magnetically attract each other, how should I connect the second battery to the second solenoid? To solve this problem, I again need to use both the agent and object hand rules, like this. So because of how the battery is attached, I know the current is going to go this way. And now I can use my agent hand rule to figure out that since the wire is bending behind and the current's going this way, the magnetic field here is like this. So that means this is the north side of the solenoid and this is the south side of the solenoid. If I want these two solenoids to attract each other, then this side of this solenoid has to be the opposite of that one because opposites attract. So this has to be north and this has to be south. So I need a field that's going this way. That is in the same orientation as the first side, and the coiling is the same too. So that means my battery must be set up the same way. These two solenoids will attract each other. Here we have an electron that is moving to the right. And there's no electric field, so he's just going to move at a constant speed. But over on the other side of the board, I'm going to put an agent's X field. And what we're going to do is we're going to let this electron wander in here, and let's see what happens to him. So by the time he goes in a straight line across the first half of the board, but once he gets in here, I can use the object hand rule to see what happens to him. So using my left hand, because he's negative, my thumb is going to the right, my fingers are going into the board because of the X's, and the force that he feels at that point is downward, okay? Now, he's not just going to move straight down, he's got momentum to the right, and so what he's actually going to do is he's trying to go right, but he's being pushed down, so he ends up going a little bit in a curve, okay? And now I can do my hand rule again. Now he's moving at this diagonal direction. The force on him, or my fingers are still X's, the force on him now is this way, okay? And that's going to make him turn again. He's trying to go sort of, southeast, and then the force on him is southwest, so now he's going to end up turning and go this way. And I can do my object hand rule again. And now my thumb is going down, my fingers are going in, and the force is now straight to the left. And that's going to bend him one more time, and he's going to go this way. And then I can do the object rule again. So my thumb is going in the direction of the black vector, my fingers are in the direction of the red vectors, and I get a new green force vector that's this way. And that causes my electron to go this way, and he comes right back out. So what this is showing is the idea of magnetic steering. If I send a charged particle into a magnetic field, the magnetic field will turn the electron around and kick him back out. When we were talking about forces in September, we said that forces can do two things. You can use them to change the speed of a particle or change the direction of a particle. Both of those things count as accelerating the particle. In this case, the speed of the electron isn't changing, but his direction of his velocity is changing. This is very similar to how we used the mallet to make the bowling ball go in a circle, or how we used a string to make a tennis ball go in a circle.